Can COVID-19 visualizations influence our beliefs about the pandemic risks to ourselves and others? That's what I'm going to be talking about today. My name is Dr. Lace Padilla. I'm a cognitive scientist, and I'm going to be sharing the results of a study that we recently published on COVID-19 data visualizations. Let's begin with an example. Here we have a visualization produced by the Reich Lab that shows instance of weekly deaths here on the Y, time plotted along the X. And notice that I'm not telling you the year that this data is from or the state that this data is pulled from. But what I'd like you to do is to notice that this is the initial forecast state. And if you look over here, this is the forecasted information. We're looking at a 2-week forecast, and I'm showing you the mean of an ensemble prediction, meaning that they take multiple different models from different modeling groups that have different initial conditions and different assumptions, and they plot the mean of all of those models. Now, I want you to look at this and answer the question, is the COVID risk in the US decreasing, increasing, or staying the same? If I'm looking at this, I'd probably say it's probably staying the same when I just see the mean. But we can change the visualization technique to include some uncertainty. In this version, it has 50% confidence intervals. Let's answer the same question. Is the risk decreasing, increasing, or staying the same? I would say still probably staying the same, just a little less certain. If we go ahead and add 95% confidence intervals, we're starting to see that our judgments might be changing. And it appears as if the risk could be staying the same, but maybe increasing or decreasing. One alternative approach is one of my favorite methods, which is to show more of the underlying data, which can give you a sense of the distribution of the information that is being conveyed. What I'm showing you here are all of the models that were used to create those summary visualizations on the previous slide. The reason that these models differ is because they have different initial conditions and different assumptions about what will happen in terms of COVID. Now, the really amazing part of showing people this type of information is that our eyes and our mind are really well adapted to finding patterns in complex data like this. For example, you might notice that this distribution is a little bimodal. There seems to be clusters at the top and some clustering down at the bottom. And our visual system can also find the central tendencies among the clusters. It is important to note that this fine-grained information, that there are potentially 2 very likely possible directions that the risk could be going, is not conveyed whatsoever in the summary visualizations. The summary visualizations average over all of that probabilistic space, and they can hide important features of the data. However, even if you do use a distributional visualization like this, you still have to design it with care. For example, this particular visualization is not a very good one. The lines are all on top of each other, making it very difficult to see any individual line. And maybe you care about a specific model, and it'd be very hard to pick out a single model from this visualization technique. That leads me to a technique that I've been advocating for recently, which is intelligently selected models. So here we have a visualization that shows a subset of all of the possible models, and they were selected for the properties of the modeling procedure and to represent important features of the distribution. The reason I showed you all of these different visualizations is that it could be the case that your beliefs about the COVID-19 risk to yourselves and others might change based on which one of these you happen to see. And the truth is that you don't get a choice when you're watching the news or online in terms of which ones you're exposed to. So it is important to understand the implications of each of these different techniques. For example, if you're shown this mean forecast in Alabama, you might be very surprised when the deaths in this area increase dramatically. But if you had been showed the distributional visualization, you might be more aware that a steep increase in deaths was possible. To be clear, this visualization here is a distributional visualization that includes multiple models, and these 3 here are summary visualizations that average over that space using various principles. Now, the 2 on the right show intervals of various sizes, and I want to be clear that there's nothing special about specific size of an interval. We often see 95% confidence in scientific research, but there's nothing inherently meaningful about that particular value. For example, the National Hurricane Center uses a 66% confidence interval, and the International Panel on Climate Change uses 90% confidence. This is why we're interested on the impact of intervals at various sizes. Now, I've demonstrated to you that COVID-19 visualizations could have an impact on our beliefs about the COVID risk to ourselves and others, but we don't know that for sure. We have to study that experimentally to determine if that is truly the case. So our research question is, do COVID-19 visualizations influence our risk perception? And our second question is, do some visualization techniques have more of an impact than others? To study this, we conducted an online experiment in October of 2020, where we showed different groups of participants real COVID-19 data from that particular moment in time. The first two columns are the control. The first column shows only historical data, COVID-19 data, with no forecast, and our other control showed no uncertainty. So we just showed the mean of the ensemble. These middle columns here show summary visualizations, and this final series of columns show distributional visualizations. The other important visual feature that we wanted to examine is the scaling of the y-axis. An incident y-axis scaling is shown here in the top row, which is where they count up all the deaths that happened in California over a 2-week period, and they plot those. You could also show the exact same data with a cumulative y-axis. In this case, the deaths in California were added up over time. We conducted this experiment with 60 groups of people where each participant only saw one type of these COVID-19 visualizations, and there were 75 people per group. That was a total size in our first experiment of 1,200 participants. We conducted this experiment online with people who currently lived in California, and the sample was representative, meaning that it matched the demographics of the US population. Now, I'm not going to show you the data from all of these different groups, but I'm going to highlight some of the most interesting findings to share with you. Let's look at a few of these more closely. Here we have a visualization that has the incident y-axis and a 50% confidence interval. We can show the exact same data, but with a cumulative y-axis, and it looks like this. Intervals are very small. This visualization uses an incident y-axis, and we have 6 models that were selected by a modeling expert on our team. And these particular models have minimal model assumptions about the COVID risk moving forward. And here's the exact same data, but using a cumulative scale. We have a version where we show all the underlying data with an incident y-scale and also with a cumulative scale. Here's an example of some of the questions that we asked participants. We asked them 4 different types of questions. An example of the first one is, how often do you think each of the following people will come in contact with someone currently infected with COVID-19 in the next 2 weeks? And they had to make that decision for themselves, an average 22-year-old in their state and an average 78-year-old in their state. They also had to answer similar questions about contracting COVID-19, having severe effects from COVID-19, and risk of hospitalization as a result of COVID-19. Now, we had people do these risk judgments before they saw any of the visualizations, just right at the beginning of the experiment. Then they saw one of the visualizations for 2 minutes, and they weren't allowed to progress until they had viewed the visualization for 2 minutes. And then we asked them the exact same risk judgments. We didn't change anything about those risk judgments whatsoever. In addition, we collected measures of age, gender, education, COVID-19 risk factors based on the CDC, graph literacy score, their knowledge about COVID-19, if they had contracted COVID-19 or had been tested. Now, the results that I'm about to show you on the next slide account for all of these very meaningful factors, and what you will see is over and beyond all of these meaningful elements in our model. If you're interested to learn more, you can take a look at our supplemental material, which details the impact of all of these factors specifically. We'll begin with the cumulative y-axis and looking at the data for the visualizations that showed the mean, the 50% confidence intervals, 6 models and all models. And we have the risk ratings here on the x-axis. This is what the data looked like before people saw any of the visualizations, and here's what it looked like after viewing one of the visualizations. The first thing to note is that for these 2 visualizations, the distributional ones, the visualizations increased risk perceptions meaningfully. Whereas for these 2, the mean and the 50% confidence interval, there was no meaningful impact of visualization exposure whatsoever. This is our first piece of evidence that visualizations can change our perceptions about the COVID risks to ourselves and others, but mostly for these distributional visualizations. And these dotted lines here represent the average of the pre and post visualization exposure for all of the visualizations with the cumulative y-axis, not just the ones that I'm showing you here. And we compare this to the incident y-axis. And what we find is that there's no meaningful impact of visualization exposure whatsoever. In fact, the largest effect that we find is the difference in pre-visualization exposure risk ratings for the cumulative y-axis, shown here in the dotted lines, compared to the incident y-axis, which really has no effect at all. And we wanted to know why we're finding effect for the cumulative y-axis, but not the incident y-axis. So we went back and looked at our data visualizations, and we noticed something interesting. You might have already seen it. For the incident axis, it just so happened that at the time in California, COVID deaths were dropping, but of course the cumulative y-axis was going up. So at this point, there is a confound in our experiment. And so we wanted to run a second study to disambiguate the effects of the cumulative versus incident scale and the direction of the trending data. At this point, it was December of 2020, and the trend in California was going up for both incident and cumulative death in this area. But for New York, they had a different trend. Because they had an early spike in COVID, their incident deaths were relatively flat, as well as their cumulative deaths. So we went ahead and ran the exact same experiment as before, but we conducted the experiment with people in California and New York. And here's what the data looks like for that experiment. And I'm adding the plots here so you can remember the trends of each of these data sets. To begin, there was no meaningful exposure for any of the New York data, which makes sense because most recent trend was relatively flat in those plots. In the California data, with a steep upward trend, we're seeing the largest differences pre to post visualization exposure for all the visualization types. And importantly, we replicated the previous finding that we're seeing significantly larger changes for people who viewed the 6 models compared to the other visualization techniques. This leads us to our visualization recommendations. Cumulative y-axes lead to less variable judgments. Unfortunately, the incident y-axis scaling can be artificially manipulated, which will have real impacts on our beliefs about our COVID risk. For example, if a new testing center opens, it might seem as if there's a steep upward trend. Or if it's a holiday and people aren't getting as much testing, it might show an artificial downward trend. And all of those fluctuations are going to have meaningful impacts on our risk perceptions. With distributional data, consider using distributional visualizations. Our results indicate that the 6 model visualization and all models had the largest impact on risk perceptions, and this is consistent with prior work finding the efficacy of these distributional visualization techniques versus summary visualization techniques. In closing, I'd like to thank all of my wonderful co-authors of this work, and I hope I've given you lots of evidence that visualizations of pandemic data can fundamentally change our COVID-19 risk perceptions.